Hello! Welcome back to Primitive Recursive March? In this video, I'd like to talk about a very surprising result involving primitive recursive functions from Mazzanti's 2002 paper, Plain Bases for Classes of Primitive Recursive Functions. Specifically, there's some very nice set of functions that generates the primitive recursive functions under composition. This video builds off of my previous video on Jones and Matyasiewicz's 1982 paper, Exponential Diophantine Representation of Recursively Enumerable Sets. It's been really neat to see how the argument in this paper adapts and builds off of the argument in the 1982 paper, to the point where I was able to take an improvement made in this paper and use it to neaten up the argument from the 1982 paper. I'll try to make this video pretty self-contained, but at one point I will need to appeal to that previous result. I'm assuming you've seen my other videos on the primitive recursive functions, but just to remind you of the broad intuition, a primitive recursive function is one that can be computed by a computer program that's very careful not to go into any infinite loops. Specifically, every time it starts going through a loop in the code, it declares in advance some value, and if it goes more than that many times around the loop terminates early. This includes for loops and while loops, but also includes loops caused by functions calling themselves, either directly or inside other function calls. So I found this generation result really quite shocking. A complicated computation with potentially lots of these safety loops in it, potentially nested quite deep inside each other, can be reduced down to a single line of functions composed with each other from a really nice small set. And while the primitive recursive functions aren't all computable functions, pretty much anything you would actually bother computing in real life is primitive recursive, and so can be written as such a composition. Part of this generating set is going to be the hyperoperations, operations that generalize multiplication being repeated addition and exponentiation being repeated multiplication. We start by just defining the 0th hyperoperation to be multiplication. And then the first hyperoperation is x times itself y times. This is, of course, x to the power of y. And the second hyperoperation is x to the power of itself, y times. This is kind of a power tower, or tetration, it's sometimes called. And we can continue defining the nth hyperoperation as repeated application of the n minus first hyperoperation in this particular way. This sort of defining a function in terms of iterated application of previously defined functions, where the number of times applied is one of the inputs, is exactly the sort of thing that primitive recursive functions capture, and the hyperoperations are key primitive recursive functions. For completeness, we should also include the minus first hyperoperation, addition, and the minus second hyperoperation, successor. These don't quite follow the pattern of the other hyperoperations, but the basic idea is there. Addition is repeated successor, multiplication is repeated addition. For clarity, I'll use traditional notation for addition, multiplication, and exponents instead of any hyperoperation notation. One of the key characterizations of the primitive recursive functions is that they're exactly the computable functions on the integers which can be computed in time bounded by a concrete hyperoperation expression, some sort of expression involving hyperoperations applied to the inputs and constants, where the indices on the hyperoperations are constants. That is, we're not allowed to talk about the nth hyperoperation, right? We can't have a function that runs in 2 nth hyperoperation 3 time. But if we had a computable function that ran in n the 5th hyperoperation, 3 the 2nd hyperoperation n time, this would be a valid concrete hyperoperation expression, and so that function would be primitive recursive by this theorem. And this will be a key characterization for this video. The result is that the primitive recursive functions are generated by the modular remainder function and the hyperoperations under multivariable composition. That is, given a primitive recursive function, we can write an expression for it involving just rem and hyperoperations and the input variables. Mazzanti and some other sources call this sort of composition superposition, but I just like to call it multivariable composition or just composition, right? We're just writing an expression involving rem and the hyperoperations. To present this proof, I'll call a function generatable if it can be written in such a way, if it can be written as a composition, as an expression just involving rem and the hyperoperations. And eventually we'll prove that every primitive recursive function is generatable. For instance, the constant 0 function is just the remainder when n is divided by n. And then we can produce higher constant functions by composing with the -2nd hyperoperation, successor. And so we don't even need to include constants in our expressions for our primitive recursive functions, because we can replace those constants by these sorts of expressions here. And of course, it's going to be convenient to just write out the constants in the same way that any time I've proved that a particular function is generatable, it's going to be convenient to use the name of that function as opposed to rewriting it from scratch. We can also define the is0 function, sometimes called negation or cosignum, that returns 1 if the input is 0, and 0 if the input is positive. This is just the remainder when 2 to the n is divided by 2, right? If n is 0, this remainder is 1, and if n is larger than 0, this remainder is 0. Now, I'm just writing 2 here, but of course, if you wanted to, you could write it as the constant 2 function, which is just the successor of the remainder when n is divided by n. So overall, these compositions are going to get quite gross. I'm just going to, once we prove that a function is generatable, I'm just going to use that function wherever I want to prove that other functions are generatable. So just like in the Jones and Matyasevich paper, we're going to want to use Diophantine equations to reason about arbitrary computations. In this case, the computation of our primitive recursive function. Right, recall the MRDP theorem that given any computer program that takes in a tuple of natural numbers and outputs a Boolean, or maybe fails to halt, there's a Diophantine equation, a multivariable integer polynomial p, such that our program outputs true on some x's if and only if there are some assignments of some intermediate variables y, making p of our x's and y's equal to 0. Now, this isn't quite what we're interested in. Our primitive recursive functions output numbers, not Booleans. But that's okay. We can relationalize. Replace a program that takes in an x and outputs a y by a program that takes in an x and a y and returns a Boolean telling us if y is the correct output for our x. We're going to do something very similar to this in this proof. And then we will use summations and the function sigma of x, which tells us the sum of the digits in binary of some number x, to hunt for solutions to the Diophantine equation representing our primitive recursive function. And thus hunt for the output of our primitive recursive function so we can make it be the output of our generatable formula. Although this process will look very much like how it did in my previous video, I'll try to go through all the details in this video as well. And I'll start by going through Mazzanti's proof that sigma is generatable, and we'll show that a number of other useful functions are generatable in the meantime. When we're talking about primitive recursive functions, we're restricting our attention to the natural numbers, but we still want to be able to talk about subtraction, hence the Monus operation, the minus sign with a dot over it. We define x minus y to be x minus y if that's a natural number, and 0 otherwise. And I claim that Monus is generatable. First, consider the remainder when 2 to the x plus y plus x is divided by 2 to the x plus y plus y. I encourage you to pause the video here and take a moment to try to figure out what this winds up being. The 2 to the x plus y is just there because we need some big number, something much bigger than x or y. If x is at least y, it goes in once with a remainder of x minus y. If x is less than y, this isn't 0, which is what we want, but we can fix that. What we're going to do is we're going to take this value and multiply by a value that's 1 if x is greater than or equal to y, because we have the right value, we just want to multiply by 1 to keep it, and multiply by 0 if x is less than y. I also encourage you to pause the video and try to figure out the remainder when 2 to the x is divided by 2 to the y. This is 0 if x is at least y, and non-zero if x is less than y. If we use our is0 function to flip that around, that's exactly what we're looking for. X minus y is the remainder when 2 to the x plus y plus x is divided by 2 to the x plus y plus y times is 0 of the remainder when 2 to the x is divided by 2 to the y. Now that we have Monus, we can do division. Of course, this is natural number division, so the quotient without the remainder, or the real number division rounded down. In particular, this is the q with x equal to qy plus r. Now r, of course, is the remainder when x is divided by y, so we can get qy just by subtracting off that remainder. Now suppose that we have some big number b, large enough that it won't get in the way, and take the remainder when bqy is divided by by minus 1. by minus 1 goes in q times with remainder q. And b doesn't actually have to be that large to make this work. 2 times x plus 2 works. We just have to make sure that we can't find any additional by minus 1s in our remainder q. Right? Q has to actually be the remainder. We can't be able to subtract off yet more by minus 1s. So, plugging in our values of b and qy, we get that q is this term here. So, quotients are generatable. Using our division and remainder tools, we can now extract digits in sums, and we'll use this tool lots of times throughout this proof. For instance, if x is large enough, n choose k is the x to the kth digit of x plus 1 to the n. Let's say we wanted to calculate 4 choose 2. We could start by taking 11 to the 4th, which is 14641, and then we need to extract the hundreds digit. So we do an integer division by 100 to put that 6 in the ones place, and then take the remainder mod 10 to isolate that 6. Now, this technique doesn't work if our base isn't large enough. If we try to use 11 to the 5th to calculate binomial coefficients, 5 choose k, we wind up getting carrying that messes up our calculations. We need to pick a larger x, like 100, and now we can read off the binomial coefficients in base 100. This sort of thing will also happen a lot in this proof. We'll need a large enough base to make this sort of technique work. And luckily, we have access to some pretty big functions to produce large enough bases. So let's do this properly. If we want to calculate n choose k, we calculate x plus 1 to the n, integer divided by x to the k, and take the remainder mod x for large enough x. And in this case, x equals 2 to the n is large enough. The next thing we want to prove is generatable is the greatest common divisor function. And in order to prove that GCD is generatable, Mazzanti considers this function here. F of AB is the sum from x equals 1 to b of the sum from y equals 2 to a plus 1 of 2 to the ab times ax minus by plus b. We can use exponent laws and factor the sums apart to get two finite geometric sums, giving us a complicated closed expression for capital F. I'd say this is generatable, but this expression isn't always an integer. The quotient doesn't usually work out nicely. But the floor of f is generatable, since the floor of the quotient, right? The floor of a quotient is just the integer quotient, which we showed is generatable. So what is this sum doing? Let's take a look at a specific example where a is 4 and b is 6. This will be a sum of a bunch of terms of the form 2 to the ab, 2 to the 24th in this case, raised to the power of 4x minus 6y plus 6. And these terms look like this. Notice that we have a bunch of negative exponents here for when ax minus by plus b is negative. These are tiny fractions. Even if these were all 2 to the 24th to the negative first, right? Even if that exponent was just negative 1, there wouldn't be 2 to the 24th of them to add up to 1. So all of these terms I've highlighted here together contribute a tiny fraction between 0 and 1 to the sum. So if we take the floor of f of ab, this will get rid of all of these terms here, leaving just the sum of the remaining terms, which are all integers. And we actually also want to get rid of these terms here, terms where it's 2 to the 24th to a positive exponent, which we can do by taking the remainder when we divide by 2 to the ab, 2 to the 24th. What's going to be left is just the 2 to the 24th to the 0 terms, the ones that aren't highlighted. Each of these is 1, so we're just, all that's left is summing up a bunch of 1s, so we get a count of the number of solutions to ax minus by plus b equals 0 in the given range. In this case, there are 2 such solutions, which is the GCD of 4 and 6. So in general, taking the floor of f of ab eliminates terms from this sum where ax minus by plus b is strictly less than 0. And then taking the remainder when we divide by 2 to ab eliminates terms where ax minus by plus b is strictly greater than 0, leaving just one term in the sum of the form 2 to the 0th for each solution to ax minus by plus b equals 0, with x between 1 and b and y between 2 and a plus 1. These sorts of linear Diophantine equations are well studied. Their solutions are exactly of the form x is b over the GCD of a and b times t, and y is 1 plus a over the GCD of a and b times t for various integers t. Only values of t between 1 and the GCD of a and b inclusive will give solutions for x and y in the desired ranges. And since this formula here counts the number of solutions, the number of times ax minus by plus b is equal to 0 in this particular range, this formula gives us the GCD of a and b. So if we take our generatable closed form for f of ab and plug it in here, we're going to get a generatable expression for the GCD of a and b. Just as in the previous video, in order to get a handle on sigma, our sum of binary digits function, we'll use the exp sub 2 function. Recall that I defined the exp sub 2 of n to be the largest k such that 2 to the k divides n. In other words, exp sub 2 of n is the exponent of 2 in the prime factorization of n. We're actually already most of the way there to proving that exp sub 2 is generatable. If we call exp sub 2 k, then 2 to the k is just the GCD of n and 2 to the n. Right? We can write our number n as 2 to the k times 3 to the something else times 5 to the something else and so on and so forth. We have its prime factorization. And of course, 2 to the n has a prime factorization that just looks like 2 to the n. And then when we take the GCD, it just takes the minimum of the exponents appearing in the prime factorization. So the exponent of 2 is going to be k, since k is the minimum of k and n. The exponent of 3 is going to be the minimum of L and 0. The exponent of 5 is going to be the minimum of m and 0, and so on and so forth. And so the GCD of n and 2 to the n is just 2 to the k, 2 to the x sub 2 of n. So if we want to show that x sub 2 is generatable, we just have to figure out how to take the log base 2 of this GCD. We have to figure out some way of extracting that k. So let's talk about generating logarithms. Suppose that we know in advance that we have two numbers, x and x to the n, for some natural number n, and we want a generatable expression in terms of those for n. And it'll be perfectly fine if the expression generates garbage, if the second input isn't x to some integer n. Using the binomial theorem, we can expand x to the n out as the sum from I equals 0 to n of n choose I times x minus 1 to the I, which expands out like this. In other words, x to the n is some multiple, s, of x minus 1 squared plus n times x minus 1 plus 1. So when we divide x to the n by x minus 1 squared, we'll get s with remainder n times x minus 1 plus 1. Provided, and this is important, that we can't pull any additional x minus 1 squareds out of this remainder. Right? The remainder has to be less than the thing that we're dividing by. We can then solve for n to get a generatable formula. The paper doesn't include the Monus 1 in the numerator. Since everything's getting rounded away, it doesn't really matter if it's there or not. So this formula here isn't a perfect logarithm. It might give us junk if we plug in a number that's not a power of x in the second argument for x to the n. And it might give us junk if nx minus n plus 1 isn't less than x minus 1 squared. But this will be enough for our purposes. And those purposes are to generate the x sub 2 function. First, we'll calculate the GCD of a and 2 to the a. And remember that this gives us 2 to the power of the answer that we want, 2 to the power of k. Now, we can't just go and use our formula to take the log base 2 of our 2 to the k to extract k. Our exponent k is likely not going to be sufficiently smaller than the base. In this case, the base is 2 for our log formula to work. What does work, though, and what the paper does, is to take the log of GCD of a 2 to the a to the a base 2 to the a. That GCD being, of course, our 2 to the k, so this is the log of 2 to the ka base 2 to the a. This gives us the same answer, k. The log of 2 to the ka base 2 to the a is still k. But now we ensure that the answer k is smaller than the base 2 to the a, so that our log formula will actually work and give us the correct answer. So this is how we can generate the x sub 2 function. And so of course, now that we know that the x sub 2 and the binomial coefficient are generatable by Kummer's theorem, the sum of digits function is generatable. Right? Kummer's theorem says that the sum of the digits of n is just the exponent of 2 in the prime factorization of 2n choose n. And I've made a separate video on this, which I'll link down below. So again, just like in the previous video, we're going to be able to do a trick with summations and digit stabilization functions to count zeros of Diophantine equations, which, due to the MRDP theorem, allows us to reason about arbitrary computations. and so in particular the computation of our primitive recursive function. So recall that the MRDP theorem, the negative result to Hilbert's 10th problem, states that if we have some sort of recursively enumerable relation phi on the natural numbers, that is to say there's some computer program that takes in some inputs and outputs a Boolean, where we treat running forever as kind of outputting false, then there's some Diophantine equation, some multivariable integer polynomial d, such that phi holds of x1 through xn if and only if there are some natural numbers y1 through yn, such that when we plug the x's and y's into d, we get 0. I've made a series of videos going through every step of the proof of this, which I'll link in the description if you're curious. Now, our goal here is going to be to take our primitive recursive function, or something like it, translate it to a corresponding polynomial d, then, given particular inputs, x1 through xn, plug them in and search for some y's, making our polynomial equal to 0. First off, one of the things we're going to need to do is put some bounds on the values of y that make our polynomial equal to 0 when they exist. So this is going to be some bounds on our search range when we're searching for zeros of d. Now, if you actually go through the proof, some of the y's are going to be dummy variables, roughly on the scale of the inputs. For instance, we can represent the relation x2 is strictly less than x1 by there exists some y such that x1 is x2 plus y plus 1. This isn't some polynomial is equal to 0, but we can rewrite this as the difference of the two sides is equal to 0, so that's okay. On the other hand, some of the y's are going to be involved in coding the run of the computation of phi. Maybe the computation is going to be encoded by some rectangular grid describing how a Turing machine's tape evolves over time. Maybe the computation is going to be encoded by a list of values in a counter machine. Either way, the maximum value of these variables is going to be something like a constant to the power of the time the computation takes squared. Since we're interested in primitive recursive relations and primitive recursive functions, there's a generatable upper bound on the time those computations take as a function of their inputs, right? Specifically, there's a hyperoperation upper bound, and thus a generatable function that gives us an upper bound on the y's used to encode the run. And actually there are some y's in the proof that are dummy variables on the scale of the run encoding the y's. Ultimately it's going to be a lot to check, but if phi is primitive recursive, there's some sort of generatable function of the x's such that we only need to check y's between 0 and that upper bound. Now, the next few steps of this proof very closely resemble the proof in the previous video, so I'm going to go quite quickly through this. If you want more detailed motivations for the steps that we're going to take, you can find those in the previous video. One of the tricky things about this proof is that the MRDP theorem lets us convert relations, not functions, into Diophantine equations. So what do we do with our primitive recursive function? The clever trick the proof does is to take our primitive recursive function, call it p of x1 through xn, and convert it to a predicate phi of x0 through xn that returns true if x0 is less than p of x1 through xn. Since p is primitive recursive, this predicate is primitive recursive. So we can use the MRDP theorem to convert it into an equivalent Diophantine representation. There exists y1 through ym such that some polynomial in all of our variables is equal to 0. Now, there's a tricky bit that I'll talk about how to deal with later, but we somehow need to ensure that for any tuple of x's, there's either 0 or 1 set of y's making our polynomial equal to 0. That is, there aren't multiple sets of y's making our polynomial equal to 0. Polynomials like this are called singlefold, but the MRDP theorem doesn't necessarily give us singlefold polynomials. I'll start by focusing on the question of how, given x1 through xn, we can count the number of tuples of x0 and y1 through ym, making our polynomial 0. If D is singlefold, once we fix x1 through xn, x0 will determine the y's, if they exist at all. So each x0 that works will give us exactly 1 0 of D. So if we can count the zeros of D, that's going to give us a count of the number of x0s less than p of x1 through xn, by the definition of phi. And there are exactly p of x1 through xn such x0s. Let's do an example. Suppose we want to calculate the integer square root function, the floor of the square root function. First, we convert our function to a predicate phi of x0 and x1 that returns true if x0 is strictly less than the floor of the square root of x1. So again, for a fixed x1, counting the number of x0 that make this happen will tell us this floor of the square root of x1. Now, we don't actually need the MRDP theorem here. We can just convert this directly to the inequality x0 plus 1 squared is less than or equal to x1, which we can convert to the Diophantine representation. There exists a y such that x0 plus 1 squared plus y minus x1 is equal to 0. And let's actually square our polynomial so it's always non-negative for convenience. And we'll call this resulting polynomial D. Now suppose, for instance, we wanted to calculate the integer square root of 20. Assign x1 to that value and count the number of zeros of D that we can find. There's 1 when x0 is 0 and y is 19. There's 1 when x0 is 1 and y is 16. There's 1 when x0 is 2 and y is 11. And there's 1 when x0 is 3 and y is 4. And that's it. For this particular x1, there are exactly 4 zeros of D. Exactly 4 pairs x0 y, making D equal to 0. And since there's only at most one y for each x0, this is exactly the count of the possible x0s, making phi true. The possible x0s less than the value of our function. So again, this count of zeros is the value of our function. And I hope it's clear now that key to this construction is the fact that for each x0, there's at most one y, making our polynomial 0. If there were potentially multiple y's for a given x0, our count of zeros wouldn't be the same as the count of possible values of x0. And again, I'll talk about how we can ensure this later on in the video. For now, I want to talk about how we can count the zeros of a polynomial in a generatable way. If you've seen the previous video, you know where this is going. The Mazzanti paper introduces a really nice function that I'm calling the digit stabilizer function, f. This is f plus from the previous video. This paper doesn't use f minus, so we're just going to call it f. The function takes in two inputs, a number of digits s and a number to digit stabilize, p, and applies this really simple function that's linear in p. Here's a table of outputs of our function if the first input is 3. For p equal to 0, the result is 63, which has a digit sum of 6. For p between 1 and 8 inclusive, the result has digit sum 3, and beyond that the pattern falls apart. In general, the sum of the digits of the output of the digit stabilizer function when p equals 0 is 2s. The outputs should all be thought of as 2s digit numbers in binary, and all those digits will be 1. For values of p between 1 and 2 to the s, the outputs will be half zeros and half ones, so a digit sum of s. And this is accomplished by making the first half of the number be the digit complement of the second half. And this is all powered by the simple observation that if you take a number that's all ones in binary, so 2 to the something minus 1, and subtract another a smaller number from it, that takes the digit complement of the smaller number. And this only works up to a point. For values of p larger than 2 to the s, the pattern falls apart. So what we're going to do is take the output of our polynomial d and digit stabilize it, where the first input is large enough that we get valid results for every output of our polynomial in the range that we're searching. And then count the digits. Each 0 of our polynomial will give us 2 s1s, and every other value will give us s1s. And so that will allow us to count the overall number of ones. That will let us count the number of zeros of our polynomial. And we need to be really clever here. Remember that the digit stabilizer function can only stabilize values up to 2 to the first input. So we need to calculate some s that will bound the number of digits of the output of our polynomial d for y's in our search range. Let's say that we're searching up to z. S can be a function of the inputs x1 through xn and also our search range z. We can find this function s by first making our polynomial d increasing in its inputs by taking the absolute value of its coefficients. Turn all of the minus signs into plus signs. And then replace any yi's in d by the upper bound of the search range z. That will make them larger, and since d is now increasing in its inputs, that will make the resulting value larger. It will give us an upper bound on d. And of course, an upper bound on d will be an upper bound on the number of digits of d. A really unnecessarily large upper bound on the number of digits of d. So the plan is this. We're going to make a table of the outputs of our polynomial d for fixed x's and letting y's range up to some maximum search range. We're then going to apply the digit stabilization function to the results and try to concatenate them together so we can take their overall digit sum. Suppose we've got this example table of values, two variables, y1 and y2, that we can plug into our polynomial. And let's say our search range is we're only interested in inputs of 0 or 1, just to keep the table small. And let's say that these are the various values of our polynomial. Again, first we digit stabilize. Each of the original numbers on the table, each of the outputs of d was between 0 and 8, so we can use the 3-digit stabilization function. This gives us numbers with 2 times 3, that is 6 digits in binary, and most of these numbers have 3 ones in their binary representation, except of course the image of 0, which has 6. Now we need to concatenate the entries of the table in some order. We need to number the cells. The most systematic way to do this is to view y2 and y1 as the digits of a number in an appropriate base. In this case 2, since y1 and y2 are either 0 or 1. But of course, if the table was longer and taller, if y1 and y2 ranged over a larger range, we'd pick a larger base. When we do this, the numbering of the cells looks like this, increasing from top to bottom and then left to right, and then front to back or along any other dimensions if this was a higher dimensional table. We'll then take 2 to the 6, 2 to the length of the entries on our table, and raise that to the indices we calculated. When we add up all of these values, it will give us our desired concatenation. Right, our first entry, 10, 10, 10, when we multiply by 2 to the 6 times 0, just gives us 10, 10, 10. When we multiply our second entry, 0, 1, 1, 1, 0, 0, by 2 to the 6 times 1, it shifts everything over 6 places in binary, so it winds up just to the left of our previous entry. When we multiply our third entry, 1, 1, 1, 1, 1, 1, by 2 to the 6 times 2, it shifts everything over 12 places in binary, so it winds up just to the left of our previous entry. And finally, multiplying by 2 to the 6 times 3 shifts our last entry, 1,0,0,0,1,1, over 18 places, just to the left of what we had before. When we add all of these together, we get the desired concatenation. And when we take the digit sum, we wind up getting 15, which is 3 more than our expected 12. Right? We're concatenating 4 values here, and each one of them usually has 3 ones in it. So we expect 4 times 3, which is 12 ones overall, except the 111, 111 gives us an extra 3 ones, and that ultimately came from a 0 of our original polynomial d. So each extra 3 ones, each extra s ones, comes from a 0 of our original polynomial, and so by counting the amount of ones more than what we expect, we get a count of the number of zeros of the original polynomial. So recall that in order to represent the integer square root function in a generatable way, we first converted it to a relation asking if x0 was less than the integer square root of x1, which we could represent as there exists a y such that some polynomial d was equal to 0, where we squared d just to make sure it always outputted non-negative numbers. And that's important. We're going to be plugging our d into our digit stabilization function, and the digit stabilization function does not like negative inputs. And now we need to search for zeros of d. We have a particular x1 in mind, and we need to search for values of x0 and y that make d 0. We'll need some strict upper bound, call it g of x1, on our search range. We'll use the same g for our search on x0 and y. We don't have to, but it's notationally easier that way. For this example, x0 and y must both be less than or equal to x1, so x1 plus 1 is a strict upper bound. Normally, in order to get this strict upper bound, you'd have to reason about how long the computation took, and then use that to give you bounds on the intermediate variables y that the MRDP theorem spits out. But luckily in this example, we have a really nice strict upper bound on our search range. We also need a digit upper bound, and I'd like this to only depend on x1. So we make our polynomial positive by switching the minus sign to a plus and plugging in our upper bounds on x0 and y. This will give us a way excessive upper bound on the number of digits of the output of d, but it's an upper bound, so we can use it in our digit stabilization function. So for given x0 and x1, consider the following sum. Let's take the outputs of our polynomial, digit stabilize them, then concatenate them together. Remember that the output of our digit stabilization function will be 2s digits long. So multiplying by 2 to the 2sy will plop these values every 2s digits apart in binary, so they won't interact with each other when we add them up. So let's try to calculate this sum for x1 equal to 5. Now, if we actually plugged 5 into our upper bound on the digits s, we'd get 3600. The outputs of our digit stabilization function would be 7,200 digits long in binary, and we'd be trying to concatenate them together. Instead, for this demonstration, let's just let s be 11, which is just large enough an upper bound on the number of digits of the output of our polynomial. So plugging everything in, we have a sum that looks like this. It's really not that bad. It's a polynomial in y times an exponential term in y. These finite polynomial geometric series have nice generatable closed form even when we allow the upper bound to be a variable. So let's look at, for various values of x0 in our search range, what this sum actually looks like. The results are 132 digit numbers in binary. Each summand has 22 digits, and there are 6 of them. So I've had to split these sums over 2 lines each. So for instance, when x0 is 1, this is the result of our summation. By default, half those 132 digit numbers will be 1s. They'll have a digit sum of 66. But Whenever our polynomial outputs 0, we'll have an extra s, an extra 11 ones added to the sum. Our polynomial is 0 here, corresponding to x0 being 0 and y being 4, and here when x0 is 1 and y is 1. We can then concatenate this entire table of values together by multiplying by 2 to the 132 to the x0 and taking the sum over x0. The result will be a 792-digit number whose digit sum is 2 11s more than the expected 36 11s. And that 2 is our count of the zeros of our polynomial, the count of the x0s less than the output of our function. That is, the output of our function. 2 is the integer square root of 5. So in general, we're going to make a table of the values of our polynomial d for fixed x1 through xn and varying x0 and y1 through ym, and then digit stabilize it with the upper bound we calculated, s. S will depend on x1 through xn, of course, but I don't actually have enough space on the slide to include that dependency. Actually, s depends on x1 through xn and the upper bound on our search range. But that upper bound depends on x1 through xn, so s ultimately just depends on x1 through xn. We give each cell an index so we can concatenate them together. x0 and the y's will range from 0 to g minus 1, where g is our strict upper bound on the search range, so we can view them as digits in base g. Again, g will depend on x1 through xn, but I ran out of room to write that. To do our concatenation, since the output of our digit stabilizer function is 2s digits long, we multiply our table entries by 2 to the 2s times the index of the entry. Then we sum over the whole table, x0 and the y's ranging from 0 to g minus 1, to concatenate everything together in binary. Now, if d was never 0, all of our digit stabilizations would have s1s in them, and there are g to the m plus 1 entries on the table, right? M plus 1 variables ranging from 0 to g minus 1. So the base digit sum will be s times g to the m plus 1. Each time d is 0, the digit stabilization has 2 s1s, s more than the s that we expect. So we have to add s times the number of zeros in our search range to the digit sum. Now, by how we constructed d equals 0 happens when and only when x0 is less than p of x1 through xn, where p is the primitive recursive function we were originally trying to calculate. So if each x0 gives us at most one y1 through ym, the count of zeros is exactly the number of numbers less than p, which is just the value of p. So if we take the digit sum of this concatenation, subtract s times g to the m plus 1, and divide by s, that should give us the value of p. All that remains is to show that we can find a generatable closed form for the sum above, and figure out how to make sure each x0 only gives us one zero, and not potentially multiple y's, making our polynomial 0. And we'll start with the latter. We appeal to the result from the previous video, from Jones and Matyasiewicz's 1982 paper, Exponential Diophantine Representation of Recursively Enumerable Sets. Just as we can use the MRDP theorem to convert an arbitrary computer program to a corresponding Diophantine equation, we can translate an arbitrary computer program phi, which takes in natural number inputs, x1 through xn, to an equivalent equality where our program outputs true if and only if there are values for a mere 3 intermediate variables y1, y2, and y3, making the equality true. Where, as we wanted, the equality is singlefold. That is, for each tuple of values of x's, there's at most one triple y1, y2, y3, making the equality true. Jones and Matyasiewicz were able to not only make the representation singlefold, but they also were able to reduce the number of intermediate variables down to 3. However, there was a cost to this. Instead of an ordinary Diophantine equation, The equation of Jones-Matyasevich is unary exponential diophanty. P and Q are built up out of integer constants, variables, addition, multiplication, and the unary exponential function 2 to the power of. Now, this is quite troublesome for our purposes. Jones and Matyasevich's construction involves nesting the 2 to the power of functions 2 levels deep, 2 to the 2 to some polynomial. But recall what we're trying to use these polynomials for. We'd like to take the polynomial we're searching for zeros of, in this case p minus q, digit stabilize it by applying what's ultimately a linear function in the second coordinate, multiply by a power of 2, and then take the sum with a variable upper bound. And we would like the result to have a nice closed form, a nice generatable closed form. Now, despite looking intimidating, most of what we have here isn't actually an obstacle to getting a generatable closed form, except terms of the form 2 to the something complicated if they show up in P and Q. I'm not aware of any nice closed formulas for finite sums of things like 2 to the 2 to the I or even 2 to the I squared. Ultimately, we'd like to take the equality that we get from the Jones and Matyasevich construction and remove any exponent more complicated than just a simple variable. And we can do this by adding intermediate variables. Jones and Matyasevich were showing off by only having 3 intermediate variables. But we don't mind having lots of intermediate variables. That just means summing over more variables, and we know how to handle that. So for each complicated exponent 2 to the f of x showing up in our expression p minus q, introduce a new intermediate variable. Let's just call it z for now. Now replace f of x in our original formula by z. So we'll just have 2 to the z where we had 2 to the f of x before. And then add in an equation that z equals f of x. This will give us multiple equations, but we can combine them using a basic sum of squares construction. If we want to assert that f equals g and p equals q, that's the same as asserting that f minus g squared plus p minus q squared is 0. So for instance, suppose the Jones and Matyasevich proof gave us that phi of x was equivalent to there existing a y1 and y2 such that 2 to the 2 to the y1 plus 1 was equal to x squared times 2 to the y2 plus 3 squared. We would introduce new variables z and w for these 2 exponents, and then replace those exponents by those variables. And then we would add in new equations telling us that those variables were equal to the exponents. And we could do this recursively if there was even deeper nesting of the exponents. We'll then combine all of our equations together with the sum of squares construction. The resulting expression is equivalent, and now we have a polynomial in our variables and 2 to the power of our variables. And this is something that we know how to find closed forms for the sums of. So ultimately, we have some expression for our concatenation of our table of digit stabilized values that looks like this. For p, some polynomial in the x's, the y's, and 2 to the various x's and y's. And I claim that this multivariable sum here has a generatable closed form in terms of g, s, and the x's. And we do this by breaking this expression apart as a linear combination of monomial terms. It doesn't really matter what's going on with the x1 through xn since we're not summing over them. There will be s's in the r's, but otherwise the q's and r's are constants. By reverse distributing, we break this sum into a product of finite monomial geometric series, which we saw have a generatable closed form in the previous video. The product of generatable expressions is generatable, so this whole thing is generatable. And then we're taking linear combinations of these, and linear combinations of generatable expressions are generatable, so our original sum is generatable. And that completes the proof. So let's summarize this construction. We start with some primitive recursive function p. Then we use the result from the Jones and Matyasevich paper with a little unpacking to find a single-fold Q that's polynomial in its variables and 2 to the power of its variables, such that x0 is less than p if and only if there are y1 through ym, making q of the x's and y's equal to 0. Since q is single-fold, counting the number of solutions for x0 and the y's will count the number of x0s, which is just the value of p. By exploiting the primitive recursiveness of testing if x0 is less than p, we can find a generatable upper bound g on the range we need to search for x0 and the y's. This step is really tedious. We need to take an upper bound on the time the computation of our primitive recursive predicate takes, then use that and an understanding of the proof of the MRDP theorem to find bounds on the intermediate variables for that construction, then use that and an understanding of the proof in Jones and Matyasevich's paper to find bounds on the intermediate variables for that construction. But it is doable. And once we have generatable upper bounds on our search range, we can find generatable bounds on the number of digits of q for our digit stabilization function. Then we find a generatable closed form for the concatenation of a table of the digit stabilizations of all the values of q we want to search through for zeros. The resulting concatenation will have a digit sum of s times g to the m plus 1 plus s times the number of zeros. So we can extract the number of zeros from that, which is the value of p that we want. And of course, don't forget that s and g, I haven't been able to write them out here, but s and g are generatable expressions of x1 through xn, so we have to plug them into the answer that we get. But actually, it's fine to just treat them as variables before this last step. And that's our generatable expression for p, a shocking result that combines our ability to bound the runtimes of primitive recursive computations, a lesser-known variation on the MRDP theorem, and the zero counting technique from that paper. And so it is that every primitive recursive function can be written as a composition of the remainder function and the hyperoperations. In some really proper sense, the nested loops necessary to construct the hyperoperations are the only nested loops necessary to compute any primitive recursive function. And it's worth noting that this proof didn't really make use of higher hyperoperations beyond exponentiation, except when bounding the search range for our intermediate variables, specifically when we needed to bound the output of our primitive recursive function and the amount of time it would take to compute our primitive recursive function. So, thanks for watching. Let me know in the comments what you learned from this video, or if you have any questions, and be kind to each other.